This is basically word problems. And when it says related rates, you'll see what that means here in just a second. And look at the example. We've got a conical tank, and it's got a volume, it's got a radius, and it's got a height. So we've got three variables in there. If we start draining water out of it, what's changing? Now see, we're talking about the derivative is what? A slope, yeah, but it's also a rate of change, isn't it? Okay, what's changing here? Is the volume changing? Yeah. Is the height of the water in there changing? Yeah. Is the radius of the circle that the top of the water is making changing?
Oh, yes.
Yeah. So all of those are changing. Now look what they're doing. They're saying we could do implicit differentiation. I could differentiate both sides of this with respect to some variable. Now, what variable? Well, the one in the notes here is picking time. So as time goes on, the volume's changing, the radius is changing of the surface of the water, and the height in that cone of the water is changing. Now look at that. What don't we know in there? We don't know the radius, we don't know the height, we don't know the volume that it started with. So they would have to give us a lot of that information for us to work a problem. Because we could answer questions like rate of change of the volume per minute. What is the rate of change of the radius per minute or per second? And through differentiation, we would be able to get those instantaneous amounts. Good so far? Sure. How hard could this be, really? It says we'll start with a basic example. I'm all about basic. So it says we got x and y. They're both differentiable, but they're functions of t. And they're related by this equation. This one here. Now it wants the derivative of y with respect to t, and then it gives us when x is 1, and then it's giving us dx dt when x is 1. So what do? We differentiate both sides. Just like yesterday, we're doing this implicitly. So on the left-hand side, what's the derivative of y with respect to t? Now I am going to use this notation for this. dy dt, and there's a little 1 there on the y, so it'd just be 1 times dy dt, wouldn't it? My x squared one is going to be 2x dx dt. Remember, we're doing everything with respect to t. Where did it go? It's constant, so it's 0. Okay, so now then, what do we know in this? We're looking for dy dt. So we're looking for that thing on the left-hand side. What do we know? We know 2. Do we know what x is? Yeah, they're telling us it's 1. Do we know what dx dt is? Yes. So the derivative of y with respect to t is 4. Now that doesn't look much like a word problem because you know what, it's not. But it's just giving us practice, kind of easing into what we're going to be doing.
I understood parts of that.
Fantastic. That is good. I'm not being a smart aleck. Okay, there's just a warm-up kind of thing, if you will. Let's look at a real word problem. And this is not a ripper of a thing.
Oh, sure.
So we drop a pebble into a pond and ripples go out, forming circles. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. This is sounding like a word problem. When the radius is at 4 feet, now that means the instant is at 4 feet. What is the total area rate of change. Okay. So we've got the area we're talking about. We've got the radius. Those are our two big things. So I'm telling you, about 3/4 of the battle here is coming up with an equation that puts these variables together. Yeah, we'll plug those in just a second. Let's not get ahead of ourselves. The hard part, and this gets back to any word problems. I can give you suggestions. I can give you hints, ways to go about it, but it just comes down to your logic. I don't think I can teach anybody logic. I really don't. Y'all are logical people. You're mathematics folks. So what kind of relationship would tie these two things together? That's the answer. Well, the area of a circle. So that formula is pi r squared, right?
That would be x plus y squared. Why wouldn't?
I only remember because of that. There's this one song that my teachers taught me.
What?
It was like pi r squared. So I was like area to.
Why would
I
you
need a circumference. I just use pi.
Why would
And for you viewers of this video, that was London Wakeman singing pi r squared. For a circle?
Yeah.
Because, and that's not a bad question, we are looking for some kind of formula that ties area and radius together. Would x and y do that? Okay. That's the best answer I can come up with. Now, we're going to get to one where x and y will actually work, pretty much. So now we differentiate both sides with respect to t again, let's say. And thank you for that rendition, London Wakeman. Okay, so the derivative of a with respect to t equals the derivative of all this stuff over here. Yeah?
Why don't we change the derivatives? If there is anything on the right side, we just put d over d.
Wouldn't that be the product rule?
Well, let's see. So the derivative of a with respect to t equals, now then, what kind of thing is pi? It's just a constant.
Yeah.
Now then, r squared, what's its derivative?
2r.
Dx dt. Because remember, r is not the variable, it's time that we're differentiating with respect to. If we were differentiating with respect to r, then r squared would just be 2r. But we're differentiating with respect to t. Okay, so I've got, and the question is saying the total area, how is it changing per unit of time?
Why does it say dA over dt on the left side, but dx over dt on the right side?
It should say, you're right, it should say dr. You're exactly right. Okay,
Wait, dA or d?
no, r squared, the derivative is 2r dr dt. Yeah,
And
thank you
on
for
the
catching
left
that.
side, it's dA over dt?
That's the derivative of the area with respect to time.
Okay, so it's comparing the derivative of the area with respect to time to the derivative of r with respect to time.
Exactly right.
Okay.
Okay, so now then, over here on this side, I've got what? 2 pi r. I'm just rearranging stuff. And we're looking for the left-hand side. Okay, now then, Jonathan, let's go back and put in what we know.
Oh, I see where I jumped the gun.
So I've got 2 pi. Well, I know those. What's r? 4. Do we know dr dt?
That would be the 1.
1. Thank you.
Why
I see how I jumped the gun.
See, the radius is changing at 1 foot per second. Okay, so now then, what do we have? We've got,
Why is dr over dt equal 1?
Because
Right here.
The rate of change is 1 foot.
I just circled it.
And a constant rate of 1 foot per second.
So the radius is increasing at a constant of 1 foot per second. That's why the dr of dt equals 1.
Exactly.
The radius is increasing. That makes sense.
Okay, so I've got what, 8 pi here? And we're talking about feet, so that'd be feet per second, because that's our units. So in other words, the area is, excuse me, increasing about 8 pi, so that's somewhere around 24 feet per second at that instant.
So that's the dA over dt.
That's correct. So the very instant, and this is instantaneous rate of change now. It's not a constant. So when the radius is exactly 4, changing at 1 foot per second, the area is changing at exactly 8 pi feet per second at that boom, that one moment in time. As time goes on, that changes, right?
Oh, section transfer.
2 times, what we've been doing, like 2 times sine, like that 2 would stay.
Yeah, that's a good example. If I had 2 times, what if f of x was 2 sine x? That 2 would stay. It's a constant multiplied times the derivative of sine x.
Oh, yeah, that makes sense.
Any constants, you can just move them to the left and say, okay, when I finally get the derivative of my function here, I can just multiply by that. Isn't that what, think about this. What if I had f of x equals 4x to the third? Now, I combined 2 things when I was showing this to you, because that's the way I learned it. But isn't this just 4 times 3x squared? Same thing. The way I learned it was that you just multiply the 3 times the 4. That's just a little shortcut. You're going to get the same thing. But really, it's that constant multiple rule. So I'm glad you asked. So pi is just a constant, just like the 2 is, and the 4. Okay. Oh boy. Let's read this one. So the question comes down to, we got volume and we got radius.
Volume,
What?
So for volume we use 4 over 3 pi r cubed.
Good.
I don't have as long as that.
That's a disappointment. Now then, that formula is actually in those pages I gave you, under the geometry page. All right, so I've got a formula that hooks those 2 things together. The reason this section is called related rates, that means these things are related to each other. In other words, as the radius changes, doesn't the volume? And vice versa? Did we leave something out? Is there a pi involved in there anywhere?
Wait.
Oh, yeah, it's
4/3 pi r.
Yeah, it's 4/3 pi r.
Okay, what?
That changes.
That changes things. Let's back up.
Let's try this again.
Yeah, scratch that.
Let's try that again.
Okay, so we got dv,
Oh,
good noise, dt,
I hope they can hear it.
I bet they can, for pi, 4/3 pi, right?
We're filming? Yeah.
Yes.
That's when we got London's song. So we got 4 pi over 3. 2r,
That's a 2, not a 3.
yeah. This is a squared up here, and this is a 3. Okay, I think now maybe we got it going. So we cancel our 3's. So we've got dv dt equals 4 pi times r squared. This is looking better. dr dt.
R equals 2.
So
2,
4.5,
16,
4 pi, 2 squared is 4. So we got 4.5 divided by 16 pi. That's how it changed. And there again, if you didn't want a fraction with a decimal in the top, 9 over 32 pi. That's better. Leaving out one crummy little number. Okay, again, the trick is finding an equation that ties these related rates, which is the topic of this section, ties them together.
It's starting to become a toss-up of what I understand and what I don't.
Join the crowd, Wyatt. I'm with you. Okay, here's one. Let's read it. Okay, a picture's going to help because this is worded a little strange.
Oh, you do? I'm still trying to figure out if we're still doing the circles.
No.
Okay. Yeah, we can do a straight line on a straight line.
No, it's a triangle.
Okay, so I've got, here's the station right here. Right? There's a tracking station. Here's our plane.
Oh, it's with height, like a vertical.
So I've got this, I've got this, and I've got
Oh, now we have to deal with
this.
sine, cosine, and tangents.
Let's see if we do.
It was a triangle.
Okay, so what do we know? We know that the distance here, 10, we know that this is 6. Right triangle, what have we got? We've got a 6, 8, 10. And this is where your idea of an x comes in here, Wyatt. We might be able to use that. Okay, so currently the plane is 10 miles from the station. That's our hypotenuse. That distance is decreasing at 400 miles per hour. How fast is the plane going?
So this is, I got these equations.
So if we call this x up here, first of all, is the height, that plane's going in a horizontal line, is the 6 mile height going to change? Okay, so let's get an equation that relates all of these things together. So,
Well,
go ahead.
we know it has an acceleration of negative 400 miles per hour. So
We do, but we're going to wait a second to plug that in. So I know d squared equals 6 squared plus x squared. I know that 6 isn't changing, but everything else in there is. So really, the thing we're calling x and the distance the plane is from the station, those are going to be changing constantly. And they're related to each other. Okay, so we're going to do d dt of d squared. What's the derivative of 6 squared?
Just
0, it's a constant. It's not changing. 2x dx dt. Check. Do I have it set up right? Okay, so the derivative with respect to t of d squared is going to be 2d dd, I'm just going to put d dt, 0, I'm going to leave it out. So then I've got 2x dx dt. Am I good so far? My 2's will cancel. Now what do we know? Now we start plugging stuff in. Do I know d?
Yes, we know it's 10.
Good. Do we know how fast it's changing?
Yes, negative, and an acceleration of negative 400 miles per hour. Miles per second. Miles per hour.
Per hour. Yeah. Do we know x?
Yes, 8.
8. And we're looking for really dx dt, aren't we?
Yeah. Distance over time.
Okay, so I've got negative 40,000 divided by 8 gives me the change in speed. Because really that top line up there, the 8, is the speed. So I've got equals negative 500.
That doesn't make sense because it's asking for speed and velocity. It can't be a negative.
Yeah, now we found velocity, didn't we? So how is speed and velocity related? So speed,
Oh, right. Velocity is speed plus a direction.
exactly. So that negative velocity means the distance from the plane going left is negative, right?
Right. It's
So speed equals velocity, absolute value.
So if it's asking for speed, then it's 500 miles per hour.
Exactly. Not so bad.
Yeah.
Again, the trick is finding a relationship between the two. Questions about that, y'all?
Surprisingly, no.
On this one back here, I'm just going to leave our wrong way in the video because it shows you can mess up pretty easy in this, and all of us did, me included. Okay, let's do another one. Oh, there's not another one. Here is a little chart, just giving you some hints about how to work these. Oh, look at this. Does this bring back memories right here? Angle of revolution, radians per...
I think it's suppressed.
Free Mother Mercy.
I think
Yeah.
it's suppressed these memories.
Yeah, a Ferris wheel's going certain... Man, we could get into those things.
Not even gonna lie, I forgot.
Yeah, blotted from your memory. Okay, so unless somebody has a question, we're done with the notes.